Okay, so we were saying for Gay-Lussac, P1 over T1 equals P2 over T2. Pressure and temperature are directly related. And so if we were to increase the temperature, the pressure would also increase. If we decrease the temperature, the pressure would also decrease. Now remember, pressure is all about collisions. So if we increase the temperature, we're giving more energy to those gases. They're going to hit each other more often. They're going to be more chaotic. They're going to create more pressure. If we cool those gases down, so if we decrease the temperature, then they're not going to hit each other as often, and so the pressure is going to decrease. Okay? So if we were to graph that, similar to how we did the other ones, I'll throw in a graph here. Let's say this is pressure, and this is temperature. And it doesn't matter if temperature were here or pressure were there, but it would look something like this. So as we increase one, the other one also increases, or if we decrease one, the other one also decreases. So they go in the same direction. The last equation that we'll do is the combined gas law. So that looks a lot like this. So the combined gas law is P1V1 over T1 equals P2V2 over T2. Okay, so we got P's, V's, and T's all in one equation. Now the beauty of the combined gas law is that you can actually just memorize this one if you're not given any of the equations. If you memorize this one, you actually will have all of the other three laws combined. So as an example, if we look at Boyle's law only deals with pressures and volumes, okay? So we assume, since there's no T in the equation, we assume that temperature is constant. Again, because there's no T in the equation, we assume that temperature is constant. So there's no need to keep track of T's if the temperature is not changing, okay? So let's say you were given a word problem that only gave you pressures and volumes. Well, then you would just ignore the T's. So if you ignore the T's in the combined gas law, you actually have Boyle's law, okay? So let's look at another example. Charles' law, as we see here, deals with volumes and temperatures. There are no P's in Charles' law, so we assume in Charles' law that pressure is constant. Okay, because again, there's no P's, so pressure is constant in that equation. So again, if you have the combined gas law, if you're given a word problem that only has volume and temperature information, ignore the P's, and now you have Charles's law. Okay, and then as the last example, just to try to also show that if you memorize the combined gas law, you actually already have all the other three laws in there. Gay-Lussac's only deals with pressures and temperatures. Okay, there are no V's in his equation, so we assume that the volume is constant. Okay, again, there's no V's, so we assume that volume is constant. So if you're given a word problem that does not have anything with volume in it, or if they say volume is constant, or if they don't give you any volume information, then that means that you actually have, if you cover up the V's, you have P1 over T1. If you cover up this V, you have P2 over T2. So we see that if you memorize the combined gas law, whatever information in the word problem they don't give you, just eliminate that variable and you have the law that you need. So let's say, two examples of how we would actually take a word problem and use the combined gas law, or use any of the laws for that matter. So let me write out an example. So let's say that we have, I'm just going to shift the camera here. So let's say in a word problem, we are given a balloon that is inside. So a balloon is inside at 25 degrees Celsius and a pressure, let's say, of 1.23 atm, which is atmospheres. And let's say we then take that balloon, so we say then balloon is placed outdoors. And if we place it outside on a day like today, it's going to be relatively cold. So let's say it's placed outside in a temperature of, let's say, 15 degrees. So our temperature is decreasing. It was at 25 degrees, now it's decreasing to 15 degrees. And the question may ask, how does the volume change? Or what is the new volume? Or sorry, pressure. How does pressure change? So if we highlight a couple things, and the word problems you'll get, it may be about a balloon, it may be about a beach ball, anything that has gas or air in it is probably something that you would see in a word problem. So what you would want to do first is you want to identify kind of the information that you're given. So we have a temperature here. This is going to be our initial temperature. We have an initial pressure here. That's going to be our pressure. Okay. Reading through the rest of it, we see another temperature. So this was our initial temperature because it started out at this temperature, and then it looks like it changed to this one. So this one's going to be T2. But then we're asking, how does the pressure change? We don't have a second pressure. So we're looking for, we don't know P2. Okay. So what equation could we use? So I'll show you both ways. If we use the combined gas law, okay, which may be a little bit easier to work with. If you use the combined gas law, we don't have any volume information, right? Nothing in this word problem said anything about milliliters or liters or volume. So we're actually just going to ignore the volumes in the equation. And that shows us that we should just be using P1 and T1 and P2 and T2, which is Gay-Lussac's law. So if we look back up here in the corner, that's Gay-Lussac's. P1, T1 equals P2, T2. If we shift back over here, that's what we see. We just have pressures and temperatures. Now, a couple things to keep in mind when we use these equations. There are some units that you have to use. Volume has to be in liters. So it's very important that your volume is in liters. So V has to be in liters. Okay? In a word problem, you might get it in milliliters. If you get it in milliliters, you have to divide the milliliters by 1,000 to get it into liters before you can put it into any V equation or volumes. Temperature has to be in Kelvin. Okay, so one thing that we noticed, we have Celsius in our word problem. That's going to be a problem. We need to convert it into Kelvin first before we can put it into the T, or the temperature in our equation. And then pressure can be in any unit. So it's up to you. You just want to be consistent on both sides. So if you're using atmospheres, you want to use atmospheres on both sides. If you're using millimeters of mercury, that's fine. Just use the same unit on both sides. But volume has to be in liters. Temperature has to be in Kelvin. Now, how do we convert temperature into Kelvin? Well, it's an easy conversion. If you take your degrees Celsius and you add 273. So degrees Celsius plus 273 will always give you the Kelvin. So let's actually plug these numbers into the equation. So I'm going to shift over here. We said that all we had was pressure and temperature information. So we're using the equation P1 over T1 equals P2 over T2. Okay. Now we have our pressure. Our initial pressure was 1.23. So I'm going to erase this and put in what we have. We have 1.23. Okay. Our final pressure we don't know, so we'll keep the P2 in the equation. T1, the initial temperature was 25 degrees Celsius. Well, let's do the little math here. 25, we have to add 273. So really, we're going to put in 298 into our equation for the temperature. So I'm going to erase this temperature 1 and put 298. It was 25 degrees, but we had to add 273 before we could put it into the T. Now T2, the second or final temperature, was 15 degrees. So let's do the math here. 273, we're going to add 15. So that's 288. So instead of T2, I'm going to put in 288. Okay, so one thing you notice, we have all our variables except for pressure. We don't know pressure. And that's how all these gas problems will work. Out of the 4 kind of things that you could substitute in for, you'll just be missing one of them. Okay, so how do we solve for this? Well, the easiest way to solve would actually be to cross multiply. Okay, so we're going to cross multiply. And if we cross multiply, we end up with 1.23 times 288. Okay, so those two times each other equals 298 times P2. So 1.23 times 288 equals 298 times P2. Well, we want to solve for P2, so all we need to do is go ahead and divide by 298. Okay, so then these guys will cross out. Okay, all we're left with then is that the final pressure, or the P2, is equal to these two multiplied together divided by 298. Okay, so let's do one more. Okay. And these word problems, believe it or not, are really straightforward. It's not meant to be tricky. They'll give you all the information you need, but it's up to you to decide which equation that you need to use. Give me a second while we write out another word problem. So let's say, as another example, let's say we're dealing with a beach ball. So let's say a beach ball with a volume, say, of 289 milliliters. In an outdoor temperature. So let's say it's a beach ball in the summertime at the beach. Let's say an outdoor temperature of 30 degrees Celsius. Okay, so we have a volume of 289 milliliters in an outdoor temperature of 30 degrees Celsius. Let's say the beach ball is placed in cool water with a temperature of, let's say, 10 degrees Celsius. What will be the new size, or the new volume, of the ball? So let me reread this. So a beach ball with a volume of 289 milliliters in an outdoor temperature of 30 degrees Celsius. The beach ball is placed in cool water with a temperature of 10 degrees Celsius. What will be the new volume of the ball? So if we notice a couple things, we got to figure out which equation we're dealing with. This right here, that is a volume amount, so this would be V1. This right here is a temperature, it's going to be T1. This right here is another temperature, this is going to be T2. But we want to know what is the new volume. We don't know that, so that's V2. And V2 is what we don't know. Okay, so it looks like we have V's and T's. So we have a volume and a temperature and a new volume that we're trying to find. So we go back here to our combined gas law equation. If you do it this way, if you memorize it this way, you can redraw this back in here. One thing that we notice is we had no pressure information. There was no P or pressure information, so we'll cross that out. Okay? So we're actually just dealing with V and T. Okay? So that would be Charles's law, deals with the volume and temperatures. So we would plug that in. So I'm just going to go up here. I'm going to use this equation we already have written. I'm just going to substitute some things in. Now remember, volume has to be in liters. In the word problem, we have it in milliliters. Temperature has to be in Kelvin. In the word problem, it's in Celsius. So we're going to have to do some conversions. So let me erase this here. Okay, so let's start with volume. The initial volume, or V1, was 289 milliliters. So that means the decimal point is here. We want to divide by 1,000, which means we can move it 3 places this way. So the actual volume we're going to put in is not 289, but 0.289. Because remember, volume has to be in liters. The initial temperature was 30 degrees Celsius, but we have to add 273. So really, we're using 303 for this temperature. Okay. Final volume, we don't know, so I'm going to keep the V2. T2 is 10 degrees. Well, we need to add 273. So really we're dealing with 283. So that's going to go here for our final temperature. Okay. Just going to erase this stuff here. We've already covered that. So if we're solving for this, we want to cross multiply. So we're going to multiply these two together and those two together. So the cross multiplication would be 283 times 0.289 equals 303 V2. And then if we want to solve for V2, we would just divide both sides by 303. Okay. And this would give us our final volume. So remember, the units for volume would be liters. So whatever this number ends up being would be in liters for your unit. Now, the combined gas law, the examples that I gave you, we actually were able to eliminate one of the variables because that information was not given. There could be a situation where you could be given pressures, volumes, and temperatures. And if that's the case, you have to keep all of the variables. So it's very likely that for a quiz, or maybe more so for the test, that you can be given an initial pressure, an initial volume, an initial temperature, and you could be given a final pressure, a final volume, and you might have to find the final temperature. So just keep in mind, if you're missing information, you can cross that out from the equation. If you're given information for all of these variables, you do have to keep all of the variables. Okay? In the next video, I'll do a video on the ideal gas law, Dalton's partial pressure, and Graham's law, or the rate of effusion.